All right, so today we're going to be diving into a world where some of the most complex problems in science and engineering get tackled.
Yeah.
And that's through the power of numerical methods,
Yeah.
specifically the Finite Element Method, FEM, and the Finite Volume Method, FEM.
These methods really are remarkable. I mean, you think
Yes.
about the challenge of, designing a skyscraper to withstand an earthquake or
Right.
modeling the intricate flow of air over an airplane wing.
Yeah.
Those are problems that'd be nearly impossible to solve using traditional analytical methods.
Absolutely. Yeah, it's mind-boggling how they even begin to approach those kinds of problems.
Right.
I mean, where do you even start when the equations are so intricate and the systems are so complex?
Well, I think at the heart of both FEM and FEM is this idea of breaking down
Right.
a massive complex problem into smaller, more manageable chunks.
Okay.
It's like taking a giant jigsaw puzzle and dividing it into individual pieces.
So instead of trying to solve the entire puzzle at once, we focus on understanding each piece individually.
Exactly.
Okay, yeah, I'm starting to see the logic here.
And this concept of discretization,
Okay,
as
yeah.
it's called, allows us to apply numerical techniques to approximate the solution within each of those smaller pieces.
So it's like trading a massive, unsolvable problem for a series of smaller solvable ones.
Precisely.
Okay,
And by carefully stitching those individual solutions together,
right.
we can build up a comprehensive picture of the overall system's behavior.
Yeah,
Now, while both FEM and FEM share this fundamental approach,
right.
they diverge in their specific mathematical formulations and areas of application.
Okay, let's dig into those differences.
Sure.
I'm curious to understand what sets these two methods apart and when you might choose one over the other.
Okay, well, let's start with FEM.
Okay,
This method is particularly well suited for problems involving solid mechanics, structural analysis, and heat transfer.
okay.
It excels at handling complex geometries and intricate boundary conditions.
So if you're designing a bridge with a unique shape or analyzing the stress distribution in a complex machine component,
Yeah,
FEM would be your go-to tool.
absolutely.
Okay,
The beauty of FEM lies in its ability to represent the solution using what are called piecewise continuous functions
okay,
within each element.
okay,
These functions, known as shape functions,
okay.
play a crucial role in approximating the solution's behavior.
Shape functions. That sounds intriguing.
Yeah,
Can you elaborate on how they work?
sure. Imagine you have a curved surface that you want to represent mathematically.
Right.
Now, instead of trying to find a single complex equation to describe that entire curve,
Right.
you could approximate it using a series of straight lines connected at specific points.
So it's like connecting the dots to create a simplified representation of the curve.
Exactly.
Okay.
And those straight lines are analogous to the shape functions in FEM.
Okay.
They provide a simple yet effective way to approximate the solution within each element.
Okay, that makes sense. So each element has its own set of shape functions that capture the local behavior of the solution.
Precisely.
Okay.
And by carefully choosing these shape functions and ensuring continuity across element boundaries,
Right.
we can build up a globally accurate representation of the solution.
This is fascinating.
Yeah.
It's like we're building a mathematical model of the system piece by piece using these shape functions as the building blocks.
That's a great way to think about it.
Okay.
Now, in contrast to FEM's focus on spatial discretization,
Right.
FEM takes a different approach,
Okay.
emphasizing the conservation of quantities within a control volume.
Control volume, I'm not familiar with that term.
Right.
Could you explain?
So imagine you're analyzing the flow of water through a pipe network.
Good.
In FEM, we divide that network into a series of control volumes.
Oh.
Think of them as imaginary boxes or cells,
Okay.
and we focus on what goes into and out of each volume.
So it's like keeping track of the water budget for each section of the pipe network.
Exactly. We want to ensure that the amount of water flowing into a volume is balanced by the amount flowing out,
Right.
plus any changes due to sources or sinks within the volume.
That sounds crucial.
Yeah,
Especially if you want to avoid any leaks or unexpected fluctuations in the system.
absolutely.
Yeah.
And this principle of conservation is fundamental to FEM.
Okay.
It ensures that we're accurately capturing the physical behavior of the system,
Right.
whether it's fluid flow, heat transfer, or any other phenomenon that involves the movement of quantities.
Okay, so FEM is all about keeping things balanced within each control volume.
Yeah.
But how does it actually accomplish that mathematically?
Well, the key lies in the integral form of the governing equations.
Okay.
Instead of solving the equations directly as we do in FEM,
Right.
FEM focuses on the integrated or averaged quantities over each control volume.
So instead of looking at the detailed behavior within each volume,
Yeah.
we're focusing on the overall balance across its boundaries.
Precisely. And by applying numerical techniques to approximate the fluxes,
Okay.
volts of flow across those boundaries,
Right.
we can ensure that the conservation principle is upheld.
This is starting to make a lot of sense.
Yeah.
FEM excels at handling complex shapes and boundary conditions, while FVM focuses on ensuring the conservation of quantities within control volumes.
Right.
It's like they each have their own strengths and areas of expertise.
Exactly.
Yeah. Now, we've been talking about these methods in a somewhat conceptual way,
Right.
but I'm curious to delve a bit deeper into the mathematical nuts and bolts.
Sure.
For example, you mentioned degrees of freedom in FEM.
Yeah.
What exactly are those, and how do they come into play?
So degrees of freedom are essentially the unknowns we're trying to solve for in our FEM model.
Okay.
Think of them as the specific points within
Yeah.
each element where we're kind of pinning down the solution.
So it's like we're creating a map of the system's behavior, and the degrees of freedom are the key landmarks that guide us.
That's a good analogy.
Okay.
And the number and location of these degrees of freedom are determined by the type of element we're using
Right.
and the overall complexity of the problem.
Okay, so the more complex the problem, the more degrees of freedom we'll need to accurately capture its behavior.
Exactly.
Okay.
And these degrees of freedom play a crucial role in assembling what's called the global system of equations
Okay.
that we need to solve.
Global system of equations.
Yeah,
That sounds pretty daunting.
it can be.
Can you shed some light on how that works?
So imagine each element is having its own little set of equations
Okay.
that describe the behavior within that element.
Right.
The degrees of freedom act as the connection points
Okay.
between these local equations,
Right.
allowing us to stitch them together
Right.
into a single comprehensive system.
So it's like we're taking all those individual puzzle pieces and assembling them into a complete picture.
Precisely. And this global system of equations represents the overall behavior of the system, taking into account all the interactions between the elements.
Wow. It's remarkable how FEM transforms a seemingly intractable problem into a solvable system of equations.
It is.
Yeah.
And the beauty is that this system of equations can then be solved using numerical methods,
Right.
allowing us to obtain an approximate solution
Okay.
for the entire problem domain.
Now, on the FEM side,
Yes.
you mentioned numerical techniques for approximating fluxes across control volume boundaries.
Right.
Can you give us some insight into how that works in practice?
Sure. One common approach is to use what are called finite difference methods,
Right.
which essentially approximate derivatives
Okay.
using the values of the variables at neighboring control volumes.
So it's like looking at the differences in water levels between adjacent sections of our pipe network
Exactly.
to estimate the flow rate.
Yeah. And there are various schemes
Okay.
for calculating these finite differences, each with its own strengths and weaknesses in terms of accuracy and stability.
It sounds like choosing the right scheme is crucial for obtaining a reliable solution.
It is.
What factors do you consider when making that decision?
Well, one important factor is the nature of the flow itself.
Okay.
Is it smooth and gradual?
Right.
Or is it highly turbulent and chaotic?
So the choice of scheme depends on how wild the water's flowing through our pipe network.
Precisely.
Okay.
If the flow is relatively well behaved, we can use simpler schemes.
Right.
But if it's highly dynamic, we might need to employ more sophisticated schemes to capture those rapid fluctuations.
Okay, that makes sense.
Right.
Another aspect I'm curious about is meshing.
Right.
You mentioned breaking down the problem into smaller elements or control volumes.
Yes.
How do you go about creating those meshes, and what considerations are involved?
So meshing is a crucial step in both FEM and FEM.
Okay.
It's the process of dividing the problem domain into a network of interconnected elements, or control volumes.
So it's like deciding how to cut up our jigsaw puzzle into individual pieces.
Exactly.
Okay.
And the quality of the mesh can significantly impact the accuracy and efficiency of the solution.
What factors influence mesh quality? Is it simply a matter of making the elements as small as possible?
Not necessarily.
Okay.
While smaller elements generally lead to higher accuracy,
Right.
they also increase the computational cost.
So it's a trade-off.
It is.
It's like trying to find the sweet spot between detail and feasibility. Too much detail and the computation becomes overwhelming.
Right.
Too little detail and we lose accuracy.
That's a great way to put it.
Okay.
And the ideal mesh often varies depending on the specific problem we're trying to solve.
So there's no one-size-fits-all approach to meshing. It's more of an art than a science.
Well, it's a bit of both, actually.
Okay.
There are certainly best practices and guidelines,
Right.
but it often involves a degree of judgment and experience
Okay.
to create a mesh that's both accurate and computationally efficient.
Okay, I'm starting to appreciate the nuances involved in meshing.
Yeah.
It's not just about blindly dividing the domain.
Right.
It's about strategically creating a mesh that balances accuracy, efficiency, and the specific requirements of the problem.
Precisely.
Okay.
And as we move towards solving even more complex problems,
Right.
the role of meshing becomes even more critical.
This is all fascinating.
Yeah.
It's incredible to see how much thought and ingenuity goes into these numerical methods, from selecting the right schemes to crafting the perfect mesh.
You're right.
It's clear that it's not just about plugging numbers into equations. It's about understanding the nuances and making informed decisions at every step of the process.
That's exactly right.
Yeah.
And the beauty is that these methods continue to evolve and improve,
Right?
allowing us to tackle increasingly challenging problems in science and engineering.
So we've been deep into the intricacies of FEM and FEM. But are these methods just confined to, the realms of academia and high-tech industries?
Well,
Or do they have tangible impacts on our everyday lives?
they absolutely impact our everyday lives.
Okay.
I mean, these methods are so deeply integrated into our technological landscape
Yeah.
that we often don't even realize their presence.
Okay, give me some examples of FEM and FEM in action, hidden in plain sight.
Sure, let's start with something as simple as, driving a car.
Okay.
The design of that car, from its aerodynamic shape to
Right.
the structural integrity of its chassis, has likely been optimized using FEM.
Okay.
It helps ensure that the car is fuel efficient, safe, and able to withstand the stresses of driving.
So FEM is helping us get from point A to point B more safely and efficiently.
Exactly.
I never thought about it that way.
Yeah. And what about the bridges we cross or the buildings we work in?
Right, yeah.
FEM plays a crucial role in ensuring their structural stability. It allows engineers to design structures that can withstand various loads and environmental conditions.
Wow, so FEM is quietly working behind the scenes to keep us safe and sound in our built environment.
Absolutely.
That's amazing.
And let's not forget about the role of FVM in predicting the weather.
Yeah.
I mean, those forecasts we rely on to plan our day,
Yeah.
those warnings that help us prepare for storms,
Right.
they're often based on sophisticated FEM models
Okay.
that simulate the complex dynamics of the atmosphere.
It's amazing to think that these seemingly abstract mathematical methods are helping us understand and predict the natural world around us.
Yeah, and they're not just limited to engineering and meteorology.
Oh.
FEM is also used in healthcare to model blood flow in arteries,
Wow.
helping doctors diagnose and treat cardiovascular diseases.
Okay.
It's even used in finance to simulate market trends and assess financial risks.
So it seems like the applications of FEM and FVM are incredibly diverse,
Oh, yeah.
spanning across numerous fields and impacting our lives in countless ways.
Precisely. They are fundamental tools
Yeah.
for understanding and solving complex problems,
Right.
driving innovation, and shaping the world around us.
Well, after this deep dive, I'm definitely looking at the world with a newfound appreciation for the power of numerical methods.
Good.
It's incredible to see how they're quietly working behind the scenes, making our lives safer, more efficient, and more informed.
And it's just the beginning.
Yeah.
As computational power continues to grow
Right.
and these methods continue to evolve,
Right.
we can expect even more groundbreaking applications and discoveries in the years to come.
Well said. It's truly an exciting time to be witnessing the power of FEM and FEM unfold and shape the future.
It is.
Thanks for joining us today and sharing your insights.
It's been my pleasure. Thanks for having me.